So I'd like to introduce the first speaker, Jonathan Chan, who's going to talk to you about is size typing for Coq practical.
All right. So yeah, I'll be presenting our work. Our JFP paper is size typing for Coq practical. And this is joint work done at UBC with Michael Lee, who is now at the University of Cambridge, and William Bowman at UBC. I'll be starting with an overview of what size types are and what they're for, then outline the key contributions in contrast to existing work on size-dependent types that are designed towards being used for Coq, and spend the remainder of the talk going over one of the key contributions, which is an implementation of size types in a fork of Coq, to explain why we think this design for size typing for Coq is not practical. So our setting here is the proof-assistant Coq and its core calculus, which is some form of CIC. So for CIC to be consistent as a logic and for type checking to be decidable, all programs must terminate. And the current method of checking termination of recursive functions is with a syntactic guardedness check, which restricts recursive calls to constructor subarguments. So this minus example you see does pass the guardedness check, since the recursive call to minus passes in n prime, which is a subargument of n. But this div example on the right does not pass the guardedness check, since the recursive call to div passes in minus n prime m, which is not a subargument of n. So Coq will do additional syntactic tricks, like unfolding the definition of minus in the body of div to get the guardedness check to pass. But this is sometimes difficult to reason about and doesn't always work. And in fact, this code as it stands does not check in Coq. But if we make a small modification like this, then it will check. Whoa. But the change that was made wasn't even in the definition of div, but in the base case of minus, so returning the first argument n rather than 0. So this strategy isn't very modular between top-level definitions. And one more disadvantage to unfolding definitions is that it can also be bad for performance if the definitions are very large. But the real reason we know that div will terminate is because minus n prime m will never return an argument bigger than its first argument n prime, because it's subtraction, and n prime is a subargument of n. So this is where size types come in, and the idea is to mark the type of minus with size annotations to indicate this, and to use this size information when type checking div in place of a guardedness check as a more expressive and more modular alternative to termination checking. So these annotations will occur on inductive types and conductive types, but we'll focus on NAT. And these annotations are either a size variable, the successor of a size, or the infinite size. And informally, the size of an inductive measures at most how large an element is, or how many layers of constructors it has. And the infinite size is used for inductives with no such bounds. So constructors will increase the size annotation, so the successor of a natural has a size that is 1 greater than that natural. And correspondingly, destructing a natural gives in the successive branch a subargument whose size is 1 smaller. So we're destructing n here with size s plus 1, and in the successive branch, m has size s. Now, the idea behind ensuring that a recursive function terminates is that you can only recursively call that function on an argument with a strictly smaller size. So for div, if we're given a natural of size v plus 1, the recursive call must be on a natural of size v. The key here is that minus doesn't increase the size of what passes through its first argument. So in the body of div, when the subargument n prime of size v is passed as the first argument of minus, We can still use the result of minus, because it also has size v, as the first argument to div. And this will satisfy the condition that div is only recursively called on an argument of size v. So far everything I've described is past work, is from past work on size types. And the totality of this literature dates back to more than 25 years. But we'll focus on these type systems in the middle, these three in the middle, that were designed specifically for adding size types to CIC and CC with co-inductives. So the vision of these type systems was to start from plain CIC code, and then through a size inference algorithm end up with a completely size annotated code. And these systems also feature nested inductives and co-inductives, and they also support type universes, including an impredicative prop. However, there's still a gap between those past type systems and fully supporting size types in Coq. So we've therefore designed a new system, CIC hat star, based on these type systems to narrow that gap and bring size types closer to Coq. There is a number of changes that this entails. One of them is that past systems require you to always annotate the decreasing argument of a recursive function, but Coq can sometimes guess which one that is. So we therefore augment size inference to also include inferring those annotations. These past systems also need polarity annotations on parameters to really support nested sized inductives and co-inductives. These are more complicated to infer, so for now we don't support them. Coq's core calculus also includes cumulativity and global and local definitions, which were missing from those past systems, so CIC hat star adds those as well. And of course, our biggest contribution is a prototype implementation of CIC hat star's size annotation algorithm, inference algorithm in the kernel of a fork of Coq 8.12. There are a few more subtle differences, technical differences between CIC hat star and past work, but ultimately this is the goal we were aiming for. We want completely backward compatible size typing for Coq, so that termination checking is expressive, modular, and efficient, especially compared to Gardner's checks. But it turns out that trying to keep as much backward compatibility as possible, which is sort of also the direction all of the past work was headed towards, leads to a lot of challenges in making type checking performant enough to be practically usable. And to see what goes wrong, we will dive into the implementation of size typing. To summarize what the implementation touches, here is a pipeline of how a top-level definition passes through the Coq kernel. Starting with a CIC term, it undergoes type checking and size inference in the same algorithm, yielding a CIC hat star term containing size variables along with a set of constraints that those variables must satisfy. We will then solve those constraints and unify some of the size variables to yield size expressions that are then substituted into the term. And this produces a CIC hat star term that will then leave the kernel. So formally, for the first half of the pipeline, we have this judgment that takes the current set of constraints, typing context, a term and a type. This is to the left of the squiggly arrow, and returns a new set of constraints along with the size annotated term and its type. In the second half of the pipeline, given a term, its type, and a set of constraints on the size variables in that term and type, these size variables will get unified so that we're left with just a size annotated term and its type. So once this term leaves type checking, it becomes part of a global definition that can be used in other terms. These definitions will range over the size variables in the terms and their types. And each use of a definition can instantiate those variables differently. As is the case with this div function that uses a custom mynat definition 3 times in its type with 2 different sizes, v and w. So onto the pipeline. Let's start with the first half of the pipeline. We'll focus on the most important rule, which is the case of typing fixed points. So a fixed point f of type tau and body e is well typed if the body has type tau with size v plus 1, while only allowed to recursively call f at size v. And to ensure that this recursive call is truly at a smaller size, we have to add the constraint that v cannot be infinite. And this step of the inference algorithm can actually run multiple times for size annotation inference, the asterisk on the tau. It runs as many times as needed to obtain 2 pieces of information. One is to figure out which argument has the decreasing size, and 2, to determine whether the output will also preserve that size. So different combinations of annotations are tried until there's one that doesn't violate the constraints or until we run out. So here in the top right, we have an example of a fixed point type that takes 2 naturals and returns a natural, and the different possible combinations of annotations. So that was the fixed point rule. Another important rule to consider is the cumulativity rule, which allows a term to be typed with a supertype, and checking that subtyping relation will also generate a set of constraints. So if we look at part of the subtyping judgment, if we're given 2 inductives of size S1 and S2, we get as output the constraint that S1 must be less than or equal to S2. And intuitively, this is because the size of an inductive represents at most how large it is. So in this example, a natural of size at most S1 also has size at most S2 if S1 is less than or equal to S2. For co-inductives, this constraint is contravariant with respect to subtyping, now representing at least how productive the co-inductive is. And in general, the form of a constraint is an inequality relation between successors of size variables. So you have v1 plus n1 is less than or equal to v2 plus n2, and so on. And where n represents how many successors there are on top of that size variable. And these are also known as difference constraints. So the most important rules stating whether a constraint is satisfiable is that a size is smaller than or equal to its successor, and that all sizes are smaller than or equal to the infinite size. There are also rules for reflexivity, transitivity, congruence, and so on. So that was the first half of the pipeline, and so far those components, that part of the size inference algorithm is all adapted from past work. So just augmented to for the features, the new features that we have for CIC hat star. In the second half of the pipeline, however, there is a new addition since it handles global definitions. From checking the satisfiability of a given set of constraints, we can obtain a size substitution from size variables to size expressions. So if we're given an annotated term and type along with a set of constraints, and these are from the first half, we could then apply the substitution that we obtain from checking the constraints to that term and type. So because the size algebra of this and most past work are simple enough that the constraints are all difference constraints, a set of such constraints can be represented as a weighted directed graph. And checking satisfiability can then be implemented as negative cycle detection such as using the Bowman-Ford algorithm, whose complexity is O of V times C, where V is the number of size variables and C is the number of size constraints. And this specifically is how we've implemented it. But there are other possibilities, such as incremental cycle detection, whose complexity can be a little lower, but still greater than linear in V and C. And so this satisfiability check is where the problems arise, because the number of variables and constraints that are involved can easily get very, very large. So here is a sort of artificial example using these 6 definitions of tuples of gnats and tuples of those tuples and so on, just to illustrate roughly what the result of size inference of these definitions might look like. Here's some of the size variables that might get generated for the gnats definitions. So that's 1 for each inductive, so the gnats and the pair types, along with a sample of the constraints that need to be checked and solved. They're at the very bottom. The exact variables aren't crucial, but what's important to note is that each use of gnats 1 in the body of gnats 2 needs its own fresh size variables for all of its sizes. And so this is how we can easily produce definitions that handle sort of exponentially many size variables with respect to the size of the terms. And you can see from this table on the right, the time that it takes to check a definition increases exponentially as well, to the point that gnats 6 will take more than 2 minutes to check. So these 6 examples are sort of contrived examples, but this isn't just a theoretical problem that only applies to pathological examples, but does affect real Coq code, especially such as when compiling the standard library with size typing. We've looked at one file in particular, msetlist, which is an implementation of finite sets using lists. And you can see that there is a 5.5x increase in compilation time with size typing versus without, and around 77% of that total time spent compiling is on operations related to checking satisfiability of those constraints. And again, this is due to the very large number of variables and constraints involved during each satisfiability check. This graph here shows its log distribution over the entire file, with buckets of the number of variables times the number of constraints along the x-axis, and the logarithm of the number of operations in each bucket along the y-axis. So although most of the time there are few variables and constraints, so the graph is mostly grouped around towards the left. There's still a non-trivial number of instances near the right where V times C can reach even up to 10 million. And that's with 4,000 variables and 2,500 constraints in the largest case. So to summarize, compilation of Coq libraries with size typing has really bad performance hits due to constraints checking and solving operations during type checking, whose runtime increases with the number of variables and constraints. And the sheer number of size variables that gets generated is due to having to generate fresh variables for every single inductive and every single use of a definition multiplied by how many size variables are in that definition. So our conclusion is that size typing for Coq will not be practical if we sort of follow the footsteps of all of the past work on size types and CIC, and insist on full backward compatibility to infer all of these sizes and constraints. But if we allow ourselves to abandon full backward compatibility, so to speak, one possibility could be to manually annotate the types of top-level definitions while still taking advantage of size inference to gather and solve constraints between those manually annotated size variables And the inferred size now meta variables in the body, such as in this example again with minus and div, where the v's and the infinite sizes are written by the user, and the question mark u and question mark w are inferred ones. In general, by specifying exactly what sizes we want definitions to range over and how, this could avoid needlessly general size variables and reduce their overall number, which could improve performance and maybe make size typing for Coq practical. But we leave all this for future work. You can check out the paper for more details and discussion, including a full specification of the size inference algorithm and a proof of soundness, some meta-theoretical results and a consistency proof attempt, and more detailed stats on the performance measurements. And we also have the now closed pull draft request that contains the implementation as well as some more discussion with members of the Coq team. Thanks for listening, and I'm happy to take questions.
To ask a question, please come up to one of the microphones. I can start. See. Question.
So, is this microphone on?
Let's try that again. Is this audible?
Yep.
Okay. On your slide where you proposed manually annotating the sizes of top-level terms, do you have a sense for, like in your MSET example, how much of the time was spent solving things specifically for top-level terms? And like, could you speculate on, if you had something like this, how much time you could possibly save with that?
I can't say for sure. I know that that file has a number of fixed point definitions, so I think this sort of thing would help, but I wouldn't know about exactly how it would help.
Cool, thank you.
Hi. So when you showed that you could use the Bellman-Ford algorithm and that it was linear in the variables and constraints, do you know that the kind of constraints that you're generating from Coq code still have this lower bound, or maybe that they're a special case that could be solved by a logarithmic algorithm or something like that?
I'm not sure. I haven't looked at the specific constraints that are generated that closely.
Thank you.
Do you have your acceptance criteria from the Coq team about what they would accept, for example? But are you allowed to impact performance at all, or does it have to be backward? Or do you have to have some meta-theoretic proof for it?
Well, I think they would like all of those things.
All of those things.
But I think performance was one of the big ones for this one.
Would they accept even a smaller negative impact, you think? Or?
Yeah, probably if it's, well, I mean, you probably couldn't avoid at least some performance impact if you want to infer some things. But yeah, a smaller impact would probably be more likely.
Between manual and automatic, did you explore having something akin to a declare directive in a file where I could state that one of my types should be sized, but I don't need the standard library to be sized?
Yeah, so the way size typing works is that there is a flag you can turn on to make some definitions sized if you want the following definitions to be sized. So the issue with not having the standard library be checked with size typing is that if for instance, you had like something like the minus definition in the standard library and you wrote your own div function and you wanted to use the standard library, then it wouldn't be sized and you wouldn't have that benefit.
Okay, I think this needs to be the last question.
This may have kind of just been answered with a previous question, but is there a way to only run the sizing analysis when the regular termination checking fails?
So, yeah, but there's still the previous problem of you might want it to sort of annotate that size preservingness from in the standard library if you want to use that property later on.
Okay, thanks.
Okay, let's move again.